Tonight, we're going to talk about a ghost. Not the kind that haunts old houses or drifts through fog on autumn evenings, but something far stranger, far older, and infinitely more patient. A ghost that may have been born alongside our own sun more than 4.5 billion years ago, and that may still be out there now, somewhere in the farthest reaches of the solar system, drifting through a darkness so complete that no telescope has ever glimpsed it. This is the story of Nemesis, the Sun's hypothetical twin, a star that might exist, a star that probably does not exist, and a star that we may never be able to prove or disprove, no matter how far our instruments reach into the black. If it is real, Nemesis would be one of the dimmest, coldest, most invisible objects in the entire galaxy. A failed star, perhaps, or a star that succeeded only barely, glowing so faintly that its light would be lost against the endless scatter of distant suns. It would be closer to us than any other star, and yet we would not know it. It would be our nearest neighbour, and yet we would never have seen its face. And if it is not real, if Nemesis is only a beautiful idea, a story we told ourselves to explain a pattern in the fossil record that turned out to be coincidence, then its absence would tell us something equally profound about the loneliness of our own sun, about the way stars are born and the way they sometimes, against all odds, end up alone. What would it mean if our sun had a sibling? What would it mean if that sibling was still out there, circling back toward us on an orbit so long and so slow that a single year of its journey would span millions of years of ours? And what would it mean if we could never find it, if the darkness was simply too deep and the light too faint, and we were left forever with only the question? By the end of tonight, you're going to understand exactly how the Nemesis hypothesis was born, why astronomers spent decades searching for a companion to our sun, what the most powerful infrared surveys in history did and did not find, and why the question remains, even now, beautifully and frustratingly open. You're going to understand the strange, almost poetic logic that connects the death of the dinosaurs to the birth of stars in distant nebulae, and why the absence of evidence is not quite the same as the evidence of absence. Before we get started, if you love exploring the deep mysteries of the cosmos as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The story of Nemesis begins not with telescopes or mathematics, but with bones. Ancient bones, buried in ancient rock, belonging to creatures that lived and died and vanished from the earth in patterns that seemed, to a handful of careful observers in the early 1980s, almost too regular to be coincidence. Paleontologists had known for decades that the history of life on Earth was punctuated by mass extinctions, sudden, catastrophic events that wiped out vast percentages of all living species and reshaped the entire trajectory of evolution. The most famous of these, the extinction that ended the reign of the dinosaurs 66 million years ago, had only recently been linked to a massive asteroid impact, a discovery that transformed our understanding of how fragile life could be in a universe filled with wandering stones. But there had been other extinctions too, the Great Dying at the end of the Permian period, the Late Devonian Crisis, the Ordovician-Silurian event, and when researchers began to look at the timing of these catastrophes, laid out across hundreds of millions of years of geological time, a curious pattern seemed to emerge. In 1983, two paleontologists named David Raup and Jack Sepkoski, working at the University of Chicago, published a paper that would spark one of the strangest scientific debates of the 20th century. They had been studying the fossil record of marine animals, compiling data on thousands of genera across hundreds of millions of years, and when they plotted the extinction rates over time, they noticed something unexpected. The peaks of extinction, the moments when life on Earth suffered its greatest losses, seemed to recur at regular intervals. Roughly every 26 million years, give or take, the fossil record showed a spike in death rates, as if some cosmic clock was striking again and again across the ages. 26 million years. The number was strange enough to be suspicious, and regular enough to demand explanation. If extinctions were caused by random asteroid impacts or volcanic eruptions or climate shifts, there was no obvious reason why they should repeat on any particular schedule. Random events by definition do not keep time, and yet here was the data suggesting that something external, something periodic, something beyond the Earth itself, might be driving these cycles of destruction. The idea caught fire almost immediately. Within a year, 3 separate groups of physicists and astronomers had proposed the same extraordinary hypothesis, arriving at it independently, each approaching the problem from a slightly different angle but converging on the same unsettling conclusion. If something was killing life on Earth every 26 million years, they reasoned, it had to be something astronomical. The only known mechanism capable of causing mass extinctions from space was an increase in the rate of comet or asteroid impacts, a bombardment from the outer solar system, a rain of icy bodies falling inward toward the sun and occasionally striking our small blue world. And if that bombardment was periodic, then something had to be causing it. Something had to be stirring up the distant reservoir of comets and flinging them toward the inner planets on a regular schedule. That something, they proposed, was a star, a companion to our sun, orbiting at an immense distance, invisible to all our instruments, completing one vast elongated orbit every 26 million years. At the far point of its orbit, it would drift in silence, too distant to affect anything. But at the near point, it would pass through or near the Oort cloud, that hypothetical shell of trillions of icy bodies believed to surround the solar system at distances of tens of thousands of astronomical units, and its gravity would disturb the delicate equilibrium of that frozen realm. Comets that had circled peacefully for billions of years would be nudged onto new trajectories, some of them plunging inward toward the sun, some of them crossing the orbit of Earth. Most of those comets would miss, of course. Space is vast and Earth is small, but over the course of a few million years the odds would shift. 1 or 2 or a dozen would find their way to our doorstep, and the results would be catastrophic. Impact craters, firestorms, dust clouds that blotted out the sun for years. The collapse of food chains, the end of eras. The scientists who proposed this hypothesis gave the star a name. They called it Nemesis, after the Greek goddess of retribution, the divine force that brought low the proud and punished the overreaching. It was a dark name for a dark idea, and it captured something of the fearful wonder that the hypothesis inspired. Here was the suggestion that our own sun, the warm and constant presence that had nurtured life on Earth for billions of years, might have a hidden twin, a cold and distant sibling, invisible and silent, that returned every 26 million years to deal out death. The hypothesis was published in Nature in 1984, in a paper by Richard Muller, Mark Davis and Piet Hutt of the University of California at Berkeley, and almost simultaneously in another paper by Daniel Whitmire and Albert Jackson of the University of Southwestern Louisiana. The idea spread quickly through the scientific community and into the popular imagination. Here was a genuinely new possibility, a hidden structure in the solar system that had escaped detection for centuries, a dark star lurking in the outer reaches of our cosmic neighbourhood. The search for Nemesis began almost immediately, but to understand why that search was so difficult and why it remains incomplete even today, we need to step back and consider what kind of object Nemesis might actually be, and why the universe seems to produce such dim and difficult companions so often. Stars, it turns out, are rarely born alone. This is one of the most consistent findings of modern astronomy, a pattern that holds across different types of stars, different regions of the galaxy, different stages of stellar evolution. When you look at the places where stars are forming right now, the great molecular clouds of gas and dust scattered along the spiral arms of the Milky Way, glowing faintly in the infrared, collapsing under their own gravity into knots and cores that will one day ignite, you find that most of them are producing not single stars but pairs, binaries, twins and triplets and sometimes larger families, bound together by gravity, orbiting one another in complex dances that can last for billions of years. The reasons for this are embedded in the physics of collapse itself. When a cloud of gas begins to contract under its own weight, it rarely does so smoothly. The cloud is turbulent, threaded with magnetic fields rotating slowly, and as it shrinks, these internal complexities express themselves. The rotation speeds up, like a figure skater pulling in her arms. The magnetic fields channel material along invisible lines of force. Instabilities develop, and the collapsing core fragments. Where there was one cloud, now there are 2 or 3 or more, each fragment continuing to contract, each one potentially becoming a star. In surveys of young stellar populations, clusters of stars that form together, only a few million years old, the binary fraction is often 50% or higher. For stars like our Sun, roughly half of all systems appear to contain at least 2 stellar companions. For more massive stars, the fraction climbs even higher. It is the rule, not the exception, that stars come with company. This makes our own Sun's apparent solitude something of a puzzle. We orbit a single star. There is no second sun in our sky, no companion rising and setting at odd angles, no pair of shadows on the ground at noon. The nearest star to us, Proxima Centauri, is more than 4 light-years away, a distance so vast that its light takes more than 4 years to reach us, and a spacecraft travelling at the speed of the Voyager probes would take tens of thousands of years to arrive. By every obvious measure, our Sun is alone, but appearances can deceive, especially in astronomy. The reason we are confident that most stars are born with companions is precisely that we can detect those companions, through the wobble they induce in their partner's motion, through the dimming of light when one passes in front of the other, through the direct imaging of closely spaced points of light in high-resolution telescopes. These methods work well for companions that are close, bright, or both. They work much less well for companions that are very distant, very faint, or both. And this is where Nemesis, if it exists, would hide. The hypothesis, as originally formulated, required Nemesis to be extremely far from the Sun, far enough that its orbital period would be 26 million years, far enough that it would spend most of its time in the cold outer reaches of the solar system, far enough that its gravitational influence on the inner planets would be negligible, except during those brief passages through the Oort cloud. The calculation suggested an average distance of perhaps 1.5 light-years, or roughly 95,000 astronomical units, nearly a quarter of the way to Proxima Centauri itself. At that distance, even a normal star would be faint, just another dim point of light in a sky already crowded with billions of them. But the hypothesis did not require Nemesis to be a normal star. In fact, the most plausible candidates were objects that were even dimmer, even harder to detect, objects that sat at the very bottom of the stellar mass scale or even below it. A red dwarf, for instance, would be a possibility. Red dwarfs are the smallest and coolest of true stars, objects with masses between about 8% and 50% of the Sun's mass. They shine with a dull, ruddy glow, emitting most of their light in the infrared rather than the visible spectrum, and they are so dim that even the nearest ones are invisible to the naked eye. Proxima Centauri itself is a red dwarf, and despite being the closest star to our Sun, it cannot be seen without a telescope. But there are objects even dimmer than red dwarfs. Below the threshold of hydrogen fusion, below about 8% of the Sun's mass, lies the realm of brown dwarfs. These are failed stars, objects that formed from the collapse of gas clouds just like their larger siblings, but never accumulated enough mass to ignite the nuclear fires that make a star shine. They glow faintly, mostly in the infrared, powered not by fusion but by the slow release of gravitational energy accumulated during their formation. They are warm, but not hot. They are luminous, but only barely, and they fade over time, cooling and dimming across billions of years, becoming harder and harder to detect as they age. If Nemesis were a brown dwarf, it would be one of the dimmest objects in the solar neighbourhood. Its light would be almost entirely in the infrared, invisible to optical telescopes. Its apparent brightness, even at a distance of only 1 or 2 light-years, would be lost in the general background of the sky. Finding it would require surveying the entire heavens in infrared light, cataloguing every faint source, and identifying any object that showed the telltale signs of proximity. A shift in position over time as it moved against the background of distant stars, a parallax that revealed it to be nearby rather than far away. This is exactly what astronomers set out to do. But the search would take decades, and the answer, when it came, would be more complicated than anyone had hoped. The first serious attempts to find Nemesis began almost immediately after the hypothesis was published, but they were hampered by the technology of the era. In the 1980s, infrared astronomy was still a relatively young field, and the instruments available were nowhere near sensitive enough to detect a faint brown dwarf at interstellar distances. Optical surveys could rule out the brightest possibilities. A red dwarf star within a light-year or two would have been noticed long ago, would have appeared in star catalogues stretching back centuries, but they could say nothing about dimmer objects. The breakthrough would come from space. In 2009, NASA launched the Wide Field Infrared Survey Explorer, known as WISE, a telescope designed to scan the entire sky in infrared light, building the most comprehensive map ever made of the cool and faint objects in our cosmic neighbourhood. WISE was sensitive enough to detect brown dwarfs at distances of dozens of light years, and it was specifically tasked with searching for any undiscovered companions to the Sun. The mission was extraordinarily successful. Over the course of its primary survey, WISE catalogued hundreds of millions of infrared sources, including hundreds of previously unknown brown dwarfs scattered throughout the nearby galaxy. It found objects so cool that they represented an entirely new spectral class, the white dwarfs, with surface temperatures not much warmer than a summer day on Earth. It pushed the boundaries of what we thought was possible in terms of detecting faint, cold nearby objects, and it did not find Nemesis. Or rather, it did not find the most obvious versions of Nemesis. The WISE survey was sensitive enough to rule out any object larger than about 5 times the mass of Jupiter within a distance of roughly 26,000 astronomical units, about 4/10 of a light year. It could rule out any object larger than Saturn's mass within about 10,000 astronomical units. If Nemesis were a star, even a small red dwarf, it would have been detected. If it were a large brown dwarf, a warm and relatively luminous one, it would have been detected. The absence of any such object in the WISE catalogue was strong evidence against the simplest versions of the hypothesis. But the universe, as it so often does, left a loophole. WISE could not rule out everything. A very cold brown dwarf, one that had been cooling for billions of years until its surface temperature dropped below the freezing point of water, would emit almost no detectable radiation even in the infrared. A planet-sized object, something more like a giant Jupiter than a failed star, would be smaller and dimmer still, and an object at the very outer edge of the proposed orbit, an object that was currently near its aphelion, its farthest point from the Sun, drifting slowly through the void at a distance of a light year or more, might be just beyond the reach of even WISE's sensitive detectors. The survey had narrowed the possibilities dramatically, but it had not closed them entirely. Nemesis, if it existed, would have to be something very specific. A cold, old, small object. Something at the boundary between a large planet and a tiny brown dwarf. Something so faint that it would be invisible even to the most sensitive infrared survey ever conducted from space. This is, in a sense, the cruelest kind of scientific outcome. Not a definitive yes, not a definitive no, but a maybe that grows thinner and thinner without ever quite disappearing. The most dramatic versions of Nemesis, a red dwarf lurking in the outer darkness, a warm brown dwarf glowing faintly as it circled back toward us, were gone, ruled out by the patient accumulation of data. But the ghost remained, a colder ghost, a fainter ghost, a ghost that had retreated further into the shadows, but a ghost nonetheless. There is something almost melancholy about this, if you let yourself dwell on it. The idea that our sun might have been born with a companion, might have spent its first few 100 million years as part of a binary system, is not merely a curiosity. It would mean that everything we know about the early solar system, the formation of the planets, the delivery of water to Earth, the bombardment of the inner worlds during the late heavy period, would have played out under the distant influence of a second star. It would mean that the sun we see today, solitary and constant, is not quite the same sun that existed at the beginning. It would mean that somewhere along the way something was lost. Stars born in binary systems do not always stay together. The gravitational dynamics of a crowded stellar nursery can tear partners apart, sending them drifting off in different directions, each one carrying the memory of its twin encoded in the subtle patterns of its motion. This is called binary disruption, and it happens frequently enough that the population of apparently single stars in the galaxy is believed to contain many former binaries. Stars that were born with siblings and lost them. Stars that have been alone for billions of years and will remain alone for billions more. If this is what happened to our sun, then Nemesis would not be a companion that still orbits us, periodically returning to stir the Oort cloud. It would be a star, or a brown dwarf, or a planetary mass object that parted ways with us billions of years ago and has since drifted off into the galaxy, as lost to us as we are to it. It would explain our sun's apparent solitude without requiring a hidden companion lurking in the outer dark. It would close the question, but it would close it with a particular kind of sadness. The sadness of a connection that once existed and no longer does, of a sibling we will never meet because they left home before we were born. The truth is that we do not know which of these stories is correct. We do not know if the Sun was born with a companion that still orbits, invisibly, at the edge of the solar system. We do not know if it was born with a companion that has since drifted away. We do not know if it was born alone, one of the minority of stars that emerge from the chaos of the nebula without a partner. The evidence is consistent with all three possibilities, and the evidence may never be strong enough to decide between them. This is one of the quiet frustrations of astronomy, the discipline of distances so vast that even light takes years to cross them, of objects so faint that the most sensitive instruments can barely detect them, of questions that can be asked but not answered within a human lifetime. We have learned so much about the universe, and yet there are still things we cannot know. Nemesis may be one of them. But let us set aside for a moment the question of whether Nemesis exists, and consider instead what its existence would mean. The original hypothesis was driven by the pattern in the fossil record, the 26 million year cycle of mass extinctions that Raup and Sepkoski had identified. If Nemesis were real, and if its orbit carried it through the Oort cloud every 26 million years, then the history of life on Earth would be intimately connected to the motion of a distant star. Every extinction, every collapse of ecosystems, every sudden reshuffling of the evolutionary deck would be traceable to a gravitational nudge from our Sun's unseen companion. The rise and fall of species, the dominance of dinosaurs for 160 million years and their sudden disappearance, the eventual emergence of mammals and eventually humans, all of it would be part of a cosmic rhythm, a dance choreographed by the slow orbit of a dark and silent star. There is something almost theological about this idea, though it is not theology. It suggests that the universe has structure at scales we rarely consider, that the patterns of life and death on our small world are echoes of patterns that span light years and tens of millions of years. It suggests that we are not isolated, not even in our apparent solitude, but connected to things we cannot see by forces we can only dimly understand. And yet the pattern that inspired the hypothesis has itself become uncertain over the decades since Raup and Sepkoski first published their findings. Other researchers, working with different datasets and different statistical methods, have reached different conclusions. Some have found evidence for periodicity in the extinction record, others have found none. The fossil record is incomplete, the dating of ancient events is imprecise, and the small number of major extinctions makes it difficult to distinguish a true cycle from a coincidence. The 26 million year period, which once seemed so striking, has come to look more and more like a statistical artifact, a pattern that emerged from noisy data and might not survive more rigorous analysis. This does not mean that Nemesis is impossible. It means only that the original argument for its existence has weakened over time. The periodicity in the extinction record, if it ever existed, may not have been caused by a stellar companion. It may have been caused by something else entirely. The oscillation of the solar system above and below the plane of the Milky Way, for instance, or random fluctuations in the rate of comet impacts that only seemed periodic because of the limited data available. Or it may not have existed at all, a mirage that vanished when better data came along. And yet the question of whether the Sun has a companion is separate from the question of whether that companion causes mass extinctions. Even if the extinction periodicity is illusory, the Sun could still have a hidden partner. Even if Nemesis has never sent a single comet tumbling toward Earth, it could still be out there, orbiting silently, waiting to be found. The search continues, in its quiet way. New surveys are planned, new instruments are being built, new methods are being developed to push the limits of detection ever further. The Vera C. Rubin Observatory, currently under construction in Chile, will conduct the most comprehensive survey of the southern sky ever attempted, cataloguing billions of objects and tracking their motions over years. It may find objects in the outer solar system that have eluded detection until now. It may find nothing. The James Webb Space Telescope, launched at the end of 2021, has already begun to study the coldest and faintest objects in the infrared, pushing into temperature regimes that were inaccessible to WISE. It is not designed as a survey telescope, so it cannot scan the entire sky, but it can follow up on hints and candidates, examining suspicious objects with a sensitivity that was unimaginable a generation ago. And there are other approaches, indirect methods that might reveal a hidden companion without directly imaging it. If Nemesis exists, it would exert a gravitational influence on the objects in the outer solar system, tugging on distant comets and trans-Neptunian objects in ways that might be detectable through careful analysis of their orbits. Some researchers have claimed to find such signatures in the data, others have disputed those claims. The debate continues, as scientific debates do, with each new observation adding another small piece to a puzzle that may never be completed. Perhaps one day, a telescope will catch a faint glimmer in the darkness, a tiny point of infrared light moving slowly against the background of distant stars. Perhaps we will discover that we were never alone, that our sun has always had a companion, that the loneliness we perceived was only our own failure to look closely enough. The discovery would be revolutionary, a transformation of our understanding of the solar system and its history. Or perhaps we will search and find nothing, and the absence will accumulate until it becomes its own kind of answer. Perhaps we will conclude, not with certainty but with increasing confidence, that the sun is indeed alone, one of the minority of stars that formed without a partner and has remained solitary ever since. Perhaps we will learn to accept that some questions, even very old and very beautiful questions, do not have the answers we hoped for. Either way, there is something profound in the asking. The Nemesis hypothesis, whatever its ultimate fate, has forced us to consider our place in the universe in a new light. It has reminded us that the solar system is not a static thing, not a clockwork mechanism ticking predictably through eternity, but a dynamic and evolving system, shaped by forces we are only beginning to understand. It has reminded us that the history of life on Earth is not separate from the history of the cosmos, but woven into it, connected by threads of gravity and light and time, and it has given us a beautiful image to contemplate on nights like this, when the sky is clear and the stars are out and the mind drifts toward the distant and the unknown. The image of a dark companion, a ghost star circling slowly through the outer reaches of the solar system, closer to us than anything else in the universe and yet utterly invisible, utterly silent, utterly alone. Whether it exists or not, the thought of it is enough to make you pause, to make you look up at the night sky with new eyes, to make you wonder what else might be hiding in the darkness just beyond the reach of our light. And so we return, tonight, to that question of hiding, to that thought of the unseen, and we let it settle around us like a familiar blanket. Because there is something in the Nemesis hypothesis that speaks to a deeper truth about the universe, a truth that has nothing to do with whether the sun's lost twin actually exists. It is a truth about what we can know and what we cannot, and about the strange comfort that can be found in the limits of our own perception. Consider for a moment what it means to look for something in the dark. Not metaphorically, but literally. When we scan the sky with our telescopes, we are not really looking at all, not in the way we look at a flower or a face or a page of text. We are collecting photons, tiny packets of energy that have travelled across unimaginable distances to strike a detector and leave their faint impression. Each photon is a messenger, carrying information about the object that emitted it or reflected it, information about temperature and composition and motion. But the photons only tell us about the objects that are emitting or reflecting them. The objects that are too cold, too faint, too far away to send us messengers remain invisible, unknown, as if they do not exist at all. This is the fundamental challenge of searching for a dim companion to the sun. It is not that we lack telescopes, though larger telescopes always help. It is not that we lack patience, though patience is certainly required. It is that the universe is under no obligation to reveal itself to us. The universe is full of things that emit no light, or so little light that it is swallowed by the background noise, or light at wavelengths our instruments cannot detect. The universe is full of silences, and we must learn to read them. The silence of the outer solar system is particularly profound. Beyond the orbit of Neptune, beyond the scattered disk of icy bodies that marks the ragged edge of the planetary zone, lies a realm of almost unimaginable emptiness. The Oort cloud, if it exists as we believe it does, is a sphere of trillions of comets, but those trillions are spread across such a vast volume that each comet is separated from its neighbours by billions of miles. If you were standing on one of those comets, looking around, you would see nothing. No other comet would be visible to the naked eye. The sun itself would appear as just another star, bright, Yes, brighter than any other star in the sky, but still just a point of light, offering no warmth, no comfort, no indication that it is your star, the star around which you orbit in your slow, cold, endless journey. And if Nemesis exists, it lives somewhere in that vast emptiness, circling the Sun at a distance so great that a single orbit takes millions of years. At such a distance, it would receive almost no light from the Sun, perhaps 0.1% of what Earth receives, perhaps less. It would be unimaginably cold, its surface temperature dropping close to the absolute minimum that physics allows, just a few degrees above absolute zero. And in that cold, it would glow, but only faintly, only in the far infrared, in wavelengths that our eyes cannot see, and that even our best instruments can barely detect. It is worth trying, just once, to feel what that kind of cold means, what that kind of distance means. We use words like far and cold so casually that they lose their power to astonish us. But the distance from the Sun to the outer edge of the Oort cloud is something like 2 light years, which means that light, travelling at the fastest speed the universe allows, would take 2 years to make the journey. If you could somehow travel at the speed of a commercial airplane, it would take you about 3 million years to reach the Oort cloud's outer boundary. And the cold at that distance is not the cold of winter, not the cold of a freezer, not even the cold of Antarctica. It is the cold of space itself. The cold that exists when there is no source of heat at all, when all you have is the faint warmth of distant stars and the even fainter glow of the cosmic microwave background, the afterglow of the Big Bang, filling all of space with radiation at a temperature of about 2.7 degrees above absolute zero. In that cold, in that darkness, a brown dwarf would be almost impossible to detect. A brown dwarf is not a failed star exactly, though it is sometimes described that way. It is more accurate to call it a not-quite star, an object that formed in the same way as a star, from the gravitational collapse of a cloud of gas and dust, but that never accumulated enough mass to ignite the nuclear fusion reactions that power true stars. Without fusion, a brown dwarf has no internal engine, no source of energy except the heat it retained from its formation, and that heat slowly, inexorably leaks away into space, carrying the brown dwarf's warmth with it, year after year, century after century, until, after billions of years, the brown dwarf has cooled to a temperature indistinguishable from the space around it. If Nemesis is a brown dwarf, and if it formed at the same time as the Sun, about 4.5 billion years ago, then it has had 4.5 billion years to cool. The models suggest that a brown dwarf of the smallest possible mass, about 13 times the mass of Jupiter, would have cooled by now to a temperature of perhaps 400 degrees above absolute zero. That sounds warm in a way, but it is cold enough to be essentially invisible in visible light, and faint enough in the infrared to be extremely difficult to detect at the distances we are considering. But there is an even more troubling possibility, one that the WISE survey could not fully address. What if Nemesis is not a brown dwarf at all? What if it is something even smaller, even colder, even harder to find? There is a class of objects that astronomers call sub-brown dwarfs, or planetary mass objects depending on how they formed. These are bodies that are smaller than the smallest brown dwarfs, too small to have ever been close to igniting fusion, but larger than the largest planets. They occupy a strange middle ground, somewhere between Jupiter and the smallest stars, and they're even harder to detect than brown dwarfs, because they're even colder and even fainter. A sub-brown dwarf in the outer solar system, orbiting the Sun at a distance of hundreds or thousands of astronomical units, would be so cold that it would emit almost no light at all. Its surface temperature might be just a few tens of degrees above absolute zero, which means that it would glow only in the longest wavelengths of the infrared, in what astronomers call the far infrared, at wavelengths that most telescopes cannot even detect. The WISE survey, for all its remarkable sensitivity, was optimized for shorter infrared wavelengths, for objects that are a few hundred degrees above absolute zero, not a few tens. A truly cold sub-brown dwarf might slip right through its net, invisible and undetected, a ghost in the machine. Spare a thought too for the sheer difficulty of confirming such an object, even if we suspected it was there. To confirm the existence of a faint point of light in the outer solar system, we would need to show that it is moving against the background of distant stars, that its motion is consistent with an orbit around the Sun, and that its brightness and colour are consistent with a cold, substellar object at the distance we calculate. Each of these steps is challenging. The motion of an object in the Oort cloud would be glacially slow, taking years or decades to become clearly apparent. The brightness would be so faint that multiple observations would be needed just to be sure the detection was real and not a spurious artifact. And the colour, the pattern of brightness at different wavelengths, would need to be measured with exquisite precision, which is difficult when you are dealing with an object that is barely detectable at all. This is why the search for Nemesis, and for other hypothetical companions to the Sun, is such a slow and painstaking process. It is not the kind of search that produces dramatic breakthroughs, not the kind that leads to press conferences and champagne and Nobel Prizes. It is the kind of search that produces gradual refinement, slowly narrowing the possibilities, slowly pushing the limits of what we can rule out, and for many people that kind of search is not very exciting. It lacks the drama of discovery, the thrill of the reveal, but there is another way to look at it, a quieter way, and perhaps that way is better suited to a night like this. Return with me, one more time, to the beginning. The Nemesis hypothesis was born from a pattern, a rhythm in the fossil record, a suggestion that mass extinctions might occur at regular intervals. Richard Muller and his colleagues proposed that a distant companion to the Sun, passing through the inner edge of the Oort cloud every 26 million years or so, might disturb the comets there and send a rain of them cascading into the inner solar system, leading to impacts and extinctions. It was a bold idea, an imaginative idea, and it captured the public imagination in a way that few scientific hypotheses do. But it is worth remembering that the pattern that inspired the hypothesis has never been firmly established. The fossil record is incomplete, the dating of extinctions is uncertain, and different analyses have produced different results. Some researchers see a clear periodicity, others see only noise. The debate has continued for 40 years now, and there is still no consensus. The pattern that Nemesis was invented to explain may itself be an illusion, a trick of the data, a case of seeing regularity where there is only randomness. This does not mean that the Nemesis hypothesis is wrong. It is possible that a distant companion to the Sun exists for reasons entirely unrelated to extinction patterns, that it is simply a leftover from the Sun's birth, a sibling star that has been quietly circling in the outer darkness for 4.5 billion years without ever causing any noticeable effects. If the companion is on a very wide orbit, or if the orbit is relatively circular, it might never pass close enough to the Oort cloud to disturb the comets there. It might just drift on, and on, and on, a silent witness to the history of the solar system, never announcing itself, never making trouble, never doing anything at all except existing. There is one more thing worth understanding about why this question matters, why scientists have spent decades trying to answer it, and why the search continues even though no clear evidence has ever been found. It matters because of what it would mean about the Sun, about our star, about the star that makes life on Earth possible. If the Sun has a companion, then it is not the solitary wanderer we have always imagined it to be. It is part of a pair, or perhaps part of an even larger system, a small stellar family drifting together through the galaxy. This would change our understanding of the Sun's history, of how it formed and how it evolved. It would raise new questions about the stability of the solar system over billions of years, about whether the companion has ever had gravitational effects on the planets, or the comets, or even on the Sun itself. It would connect us, in a new way, to the broader population of binary and multiple star systems that dominate the galaxy. And if the Sun does not have a companion, if we eventually conclude with high confidence that it has always been alone, then that too is a significant finding. It would place the Sun in a minority, a select group of stars that formed without partners and have remained solitary throughout their lives. It would raise its own questions about how the Sun managed to form alone, or about what happened to the companion it might once have had, whether it was torn away by a passing star or ejected in the chaotic early years of the solar system's formation. Either answer tells us something important. Either answer changes our picture of where we come from and who we are. And in the meantime, while the question remains open, while the search continues, we are left with the uncertainty itself, which is its own kind of knowledge, its own kind of truth. Let us sit for a long moment with that uncertainty, because it is not a comfortable thing for most of us. We live in a world where information is abundant, where almost any question can be answered by a quick search, where the unknown seems to shrink a little more every day. But the universe does not cooperate with our desire for closure. The universe is full of questions that cannot be answered quickly, that cannot be answered at all with current technology, that may never be answered in any human lifetime. The Nemesis hypothesis is one of those questions, and there is something beautiful about learning to live with it, about learning to carry the uncertainty gently, without frustration, without impatience, without the need to resolve it before we are ready. Picture, if you can, what it would be like to stand on a world in the outer solar system, far beyond Neptune, far beyond Pluto, at the very edge of the sun's dominion. The sun would be a bright star, the brightest star in the sky, but it would no longer look like a sun. It would look like a point of light, brilliant and cold and impossibly far away. The sky around you would be filled with other stars, thousands of them, millions of them, the familiar constellations stretched and distorted by your changed perspective but still recognizable, still the same stars that shine above Earth on a clear night. And somewhere in that sky, invisible to your eyes, too faint to register on any instrument you could carry with you, there might be another point of light, another star, another sun. It might be closer to you than any of the visible stars, closer than Alpha Centauri, closer than Sirius, closer than any of the familiar names that dot our star maps. It might be your nearest neighbour in the entire universe, and yet you would never see it. You would never feel its warmth. You would never know it was there. This is the strange truth at the heart of the Nemesis hypothesis, a truth that persists whether Nemesis exists or not. We are surrounded by darkness that our light cannot penetrate. We are surrounded by presences that our senses cannot detect. The universe is not obliged to make itself visible to us, to reveal all its secrets to any observer who cares to look. It keeps its own counsel, and some of what it knows, it keeps forever. There is a smaller, quieter story woven through all of this, a story about the people who have spent their careers looking for things that might not exist. Richard Muller, who first proposed the Nemesis hypothesis, with his colleague Mark Davis and the paleontologist David Rope, continued to work on the problem for years afterward, refining the theory, responding to criticisms, adjusting the parameters as new data came in. He was not alone. Other astronomers took up the search, scanning the sky with whatever instruments were available, hoping to catch a glimpse of the elusive companion. They built careers around the search, wrote papers, trained students, gave talks at conferences, and for all their efforts they found nothing. The companion, if it exists, remained hidden. It is easy to see this as a failure, as a waste of time and resources, as a scientific dead end. But that is not how science works, not really. Every search that finds nothing narrows the possibilities. Every null result rules out a range of hypotheses, pushes the limits of detection a little further, prepares the ground for the next search. The astronomers who looked for Nemesis and did not find it were not failing. They were mapping the darkness, charting the boundaries of the unknown, doing the slow and unglamorous work that makes discovery possible. And we cannot leave this story without acknowledging the peculiar courage that this kind of work requires. To spend years searching for something that you may never find, to wake up every morning knowing that today, like yesterday, might bring only more emptiness, more silence, more of the same inconclusive data that has accumulated for decades. It takes a certain kind of person to do this work, a person who is comfortable with uncertainty, who can find meaning in the search itself rather than only in the result. The people who look for Nemesis are in their own quiet way explorers, venturing into territory that no one else can see, mapping a landscape that may turn out to be entirely empty. The night is getting deeper now, and the stars are getting brighter, and the thought of that dark companion is settling into the back of the mind where it belongs. It is not a thought that demands resolution tonight. It is not a thought that needs an answer by morning. It is a thought to carry with you, like a stone in your pocket, smooth and cool and reassuring in its weight. The companion may be out there, circling slowly in the darkness, patient and cold and infinitely old. Or it may not exist at all, may never have existed, may be nothing more than a beautiful speculation that our instruments have slowly, gently laid to rest. Either way, the thought of it remains. The thought of something out there, just beyond the reach of our light, just beyond the grasp of our knowledge, drifting quietly through the same space we inhabit, sharing the same sun, bound by the same gravity, and yet utterly alone, utterly unknown, utterly beyond our capacity to touch or see or understand. This is the gift that the Nemesis hypothesis has given us, whether it turns out to be true or false. It has reminded us that the universe is larger than our instruments can measure, deeper than our theories can explain, stranger than our imaginations can encompass. It has reminded us that the darkness is not empty, even if we cannot see what fills it. It has reminded us that we are small, and that our smallness is not a tragedy but a wonder, an invitation to keep looking, to keep asking, to keep reaching out into the night. And so we reach the question that has been waiting patiently at the edge of this story, the question that anyone who has followed the search for Nemesis eventually comes to, usually late at night, usually when the stars are visible and the world has gone quiet. What if it does exist? What if, against all the silence of our surveys, against all the null results and the narrowing possibilities, there really is something out there, cold and dim and impossibly patient, drifting through the outer reaches of our solar neighbourhood? What would it mean, not for the statistics of extinction, not for the models of orbital dynamics, but for us, for the way we understand our place in the cosmos, for the way we think about home? It is worth sitting with this question for a while, letting it settle into the bones, because the answer is not what you might expect. The discovery of a stellar companion to our Sun would be, in the most technical sense, a scientific triumph. It would vindicate decades of speculation, reward generations of searchers, open entirely new fields of inquiry. The papers would multiply, the conferences would convene, the textbooks would require revision. But beneath all of that, beneath the professional excitement and the institutional machinery, there would be something else, something quieter and harder to name. There would be a kind of grief, or perhaps not grief exactly, but something adjacent to it. A recognition that we had been wrong about something fundamental, not in the details, but in the shape of our understanding. We had thought ourselves alone in a particular way, had built our sense of cosmic identity around a solitary sun, and we would have to rebuild it now to accommodate a sibling we never knew we had. This is the strange and tender heart of the Nemesis story, the part that the scientific papers cannot quite capture. We are talking about loneliness, about companionship, about the deep human need to understand whether we are alone in the darkness or whether there is something else out there, sharing our journey, bound to us by forces we cannot see. These are not scientific questions in the strict sense, though science is the tool we use to approach them. They are existential questions, questions about meaning and belonging and the shape of the universe we inhabit. And the Nemesis hypothesis, whether it turns out to be true or false, has given us a way to think about these questions, a framework for wondering, a permission to speculate. Consider for a moment what it would mean to have a companion star, even one we could never see with our naked eyes, even one that was nothing more than a dim red ember at the far edge of the sun's gravitational reach. It would mean that our solar system was not complete in itself, not self-contained, not the isolated island we had always imagined it to be. It would mean that there were forces acting on us from distances we had never considered, influences shaping our history that we had never suspected. It would mean that the story of life on Earth, with all its catastrophes and resurrections, all its extinctions and flowerings, was not entirely our own story, was not a purely local narrative, but was connected to something larger, something older, something that moved through the darkness on timescales we could barely imagine. There is something both humbling and comforting in this thought. Humbling because it reminds us how little we know, how many forces might be acting on us without our awareness, how small our understanding remains despite all our instruments and all our theories. Comforting because it suggests that we are not entirely alone, that even in our isolation we are part of something larger, connected to processes that extend far beyond our world and far beyond our comprehension. This is the paradox at the heart of the search for Nemesis. We are looking for something that might have caused great destruction, something that might have been responsible for the extinction of countless species, including perhaps some of our evolutionary ancestors. And yet there is a part of us that hopes to find it, that would be relieved to know it exists, that would feel a strange kinship with this cold and distant sibling, even as we recognized its capacity for harm. The astronomers who search for Nemesis understand this paradox, even if they rarely speak of it in their papers. They understand that the search is not just about orbital mechanics and extinction patterns and infrared surveys. It is about something deeper, something that connects to the oldest questions humanity has ever asked. Are we alone? Is there something else out there? Does the darkness that surrounds us contain companions or only emptiness? These questions have been asked in every culture, in every era, in every language that humans have ever spoken. The search for Nemesis is just the latest version of this ancient inquiry, dressed in the language of astrophysics and statistical analysis, but animated by the same fundamental curiosity that has driven every explorer, every philosopher, every child who's ever looked up at the night sky and wondered what might be looking back. And here is where the story becomes truly strange, truly beautiful in its strangeness. The companion we are looking for would not be looking back. If Nemesis exists, it is almost certainly not a place where anyone could live, not a world with observers of its own, not a star with planets that might harbour consciousness. It would be cold and small and utterly indifferent to our existence, a ball of failed fusion drifting through the darkness, unaware that billions of tiny creatures on a rocky world were searching for it with their telescopes and their equations. The companionship we would feel upon discovering it would be entirely one-sided, a projection of our own need for connection onto an object that could not care less whether we found it or not. And yet, somehow, this does not diminish the meaning of the search, it might even enhance it. There is something pure about looking for something that cannot know you are looking, about reaching out towards something that cannot reach back, about building a relationship with a companion that will never acknowledge your existence. It is a kind of love in its way, the love of the astronomer for the star that will never shine for her alone, the love of the scientist for the truth that does not care whether anyone discovers it, the love of the curious mind for the universe that keeps its secrets so well, that reveals them so grudgingly, that never offers praise or gratitude for the effort of understanding. This is the love that drives the search for Nemesis, and it is a love that does not require success to be meaningful. Return with me, one more time, to the practical question of the search, to the instruments and the techniques that have been brought to bear on this problem over the decades. Because the technology has advanced dramatically since Muller and Davis first proposed their hypothesis, and each advance has both narrowed the possibilities and revealed new ones. The story of the search is the story of a slowly sharpening picture, a gradual clarification of what we are looking for and where it might be hiding. The earlier searches were limited by the technology of their time. In the 1980s, when the Nemesis hypothesis was first proposed, infrared astronomy was still in its infancy. The ability to detect faint heat signatures from cold objects at great distances was limited, and the surveys that existed covered only small portions of the sky with relatively low sensitivity. The astronomers who looked for Nemesis in those early years were working with crude maps, searching a vast territory with inadequate tools, hoping for a lucky break that never came. They found many interesting objects, catalogued countless stars and brown dwarfs and other inhabitants of the solar neighbourhood, but they found nothing that matched the profile of the hypothesized companion. The situation improved dramatically with the launch of dedicated infrared survey missions. The Infrared Astronomical Satellite, launched in 1983, was the first to conduct an all-sky survey in infrared wavelengths, mapping the thermal signatures of objects that were too cool to emit visible light. It found many brown dwarfs, many cool stars, many objects that had never been detected before. But it did not find Nemesis. Its sensitivity was not sufficient to detect a very cold object at very great distances, and the companion, if it existed, remained beyond its reach. Later missions pushed the boundaries further. The 2-micron all-sky survey, conducted from ground-based observatories in the 1990s and early 2000s, catalogued hundreds of millions of stars and other objects, creating the most complete map of the infrared sky that had ever existed. It found brown dwarfs by the thousands, cool objects that had been invisible to earlier surveys, and it established that the solar neighbourhood was populated by many more faint objects than anyone had previously suspected. But still no Nemesis, still no signature of a companion star lurking in the outer darkness. The most sensitive search came with the Wide Field Infrared Survey Explorer, or WISE, launched in 2009. This was the mission that had been designed specifically to find the coldest objects in the solar neighbourhood, the objects that previous surveys had missed. its instruments were cooled to temperatures just a few degrees above absolute zero, giving it an extraordinary sensitivity to faint thermal emissions. It mapped the entire sky in multiple infrared wavelengths, creating a census of cold objects that was more complete than anything that had come before. And when the data was analysed, when astronomers searched through millions of candidates looking for anything that might match the profile of a distant companion star, they found many remarkable things. They found brown dwarfs closer to the Sun than any previously known. They found cool objects that challenged existing models of stellar evolution. But they did not find Nemesis. They did not find anything that looked like a stellar companion to our Sun, orbiting at the distances the hypothesis predicted. This was the result that effectively closed the door on the most dramatic versions of the Nemesis hypothesis. A Jupiter-sized object within 10,000 astronomical units of the Sun would have been detected by WISE. A Saturn-sized object within the predicted orbit would have shown up in the data. The surveys had been thorough, the sensitivity had been high, and the answer was clear. If there was a companion out there, it was either much smaller than anyone had proposed, or much farther away, or much colder than the models had predicted. The nemesis of the original hypothesis, the brown dwarf or red dwarf star that periodically disturbed the Oort cloud and sent comets raining down on the inner solar system, almost certainly did not exist. But notice the careful qualifications in that statement. Almost certainly. Much smaller, much farther, much colder. These are the escape routes that the hypothesis still possesses, the narrow pathways through which a companion might still be hiding. Because the truth is that our surveys, for all their sensitivity, are not complete. There are still objects too cold to detect, still distances too great to measure, still regions of parameter space that our instruments cannot reach. The door has been closed on the most likely versions of Nemesis, but it has not been locked, and there are smaller doors at the back of the room that remain ajar. Consider what the coldest detectable object would look like. WISE was sensitive to objects with temperatures above about 50 degrees above absolute zero, which sounds incredibly cold until you realise that the background temperature of deep space is only about 3 degrees above absolute zero, and that an object that has been cooling for billions of years might approach this temperature asymptotically. A very old brown dwarf, one that formed with the Sun some 4.5 billion years ago and has been radiating its heat into space ever since, might now be so cold that it barely distinguishes itself from the cosmic background. It would be invisible to WISE. It would be invisible to any infrared survey we currently possess. It would be detectable only by its gravitational effects, by the subtle perturbations it might cause in the orbits of distant objects, by the fingerprints it might leave on the trajectories of comets and asteroids passing through its vicinity. This is the version of Nemesis that survives the modern surveys, and it is a strange and fascinating object to contemplate. Not a failed star in the traditional sense, not a glowing ember of fusion that never quite ignited, but something older and colder, something that has had billions of years to surrender its heat to the darkness, something that is now barely distinguishable from the emptiness that surrounds it. Picture it drifting through the outer reaches of the solar system, a sphere of hydrogen and helium that contains the mass of several Jupiters, but emits almost no detectable radiation, a ghost in the gravitational sense, present only through its pull on other objects, invisible to every telescope we have ever built. There is a certain poetry in this image, a poetry that the scientists who search for such objects appreciate even if they rarely express it in their formal publications. The coldest version of Nemesis would be the ultimate expression of cosmic patience, an object that has outlasted every detection technology we have ever developed, that has hidden in plain sight for billions of years, that might continue hiding for billions more. It would be the darkness made manifest, the emptiness given form, a companion whose only proof of existence would be the subtle distortions it causes in the fabric of space and time around it. It is worth pausing on what it would take to find such an object. The gravitational methods that might reveal its presence require extraordinary precision, the ability to track the orbits of distant objects with accuracies measured in fractions of arc-seconds over timescales measured in decades. The surveys of the outer solar system that might reveal its influence are still incomplete, still limited by the difficulty of observing objects at such extreme distances. The statistical analyses that might tease out its signature from the noise of random orbital variations are fiendishly complex, subject to systematic errors and observational biases that are difficult to control. Finding a cold Nemesis would not be a matter of pointing a telescope at the right spot in the sky and seeing it there. It would be a matter of accumulating vast quantities of data over many years, analysing that data with sophisticated statistical techniques and looking for patterns that might or might not be real. This is the kind of work that does not make headlines, that does not produce dramatic discoveries or Nobel Prizes or breathless press conferences. It is the slow, patient, unglamorous work of ruling out possibilities, of narrowing the search space, of gradually refining our understanding of what might or might not be out there. The people who do this work are not looking for glory. They are looking for truth, even if the truth turns out to be boring, even if it turns out to be nothing at all. Spare a thought too for the possibility that we have been asking the wrong question all along. The original Nemesis hypothesis was proposed to explain a specific pattern in the fossil record, the apparent periodicity of mass extinctions that seem to recur every 26 to 30 million years. But the evidence for this periodicity has always been contested, has always been subject to debate and reinterpretation. Some statisticians have argued that the pattern is real, that the probability of it occurring by chance is vanishingly small. Others have argued that the pattern is an artifact of the data, a result of observational biases and statistical noise, a mirage that dissolves under careful scrutiny. If the periodicity is not real, then the original motivation for the Nemesis hypothesis evaporates. There would be no need for a companion star to explain the extinction pattern, because there would be no pattern to explain. The search for Nemesis would become a search for something that was never required by the evidence, a solution to a problem that does not exist. This does not mean the companion could not exist. It simply means that its existence would have to be established on other grounds, through other evidence for other reasons. And here is where the story takes another turn, a turn toward a different kind of mystery, a different kind of possibility. Because even if the original Nemesis hypothesis is wrong, even if there is no brown dwarf companion periodically disturbing the Oort cloud, there might still be other objects out there, other companions of a different kind, other inhabitants of the outer darkness that we have not yet detected. The solar system is a much stranger place than we once imagined, and its boundaries extend much farther than we once thought, and the census of objects in the outer reaches is still dramatically incomplete. Consider the Oort cloud itself, that vast spherical shell of icy bodies that surrounds the solar system like a second atmosphere, a frozen halo extending perhaps 2 light years from the Sun. We have never directly observed the Oort cloud. Its existence is inferred from the orbits of long-period comets, those wanderers that plunge into the inner solar system from every direction, following elongated paths that suggest origins at extreme distances. The Oort cloud is thought to contain trillions of objects, icy remnants from the formation of the solar system that were flung outward by gravitational interactions with the giant planets billions of years ago. It is the reservoir from which the comets come, the source of those spectacular visitors that occasionally grace our skies with their tails of glowing gas and dust. But the Oort cloud is so distant, so diffuse, so utterly beyond the reach of our current observational capabilities that we know almost nothing about its detailed structure. We do not know how many objects it contains. We do not know how they are distributed in space. We do not know whether there are concentrations and voids, whether the cloud is uniform or clumpy, whether there are larger objects embedded within it that might have significant gravitational effects. The Oort cloud is, in a very real sense, the largest unexplored territory in our solar system, a region that contains more mass than all the planets combined, yet remains almost entirely unknown. Picture, if you can, what it would be like to travel to the inner edge of the Oort cloud, to pass through that boundary where the influence of the distant stars becomes comparable to the influence of the Sun. You would be far beyond the orbit of Neptune, far beyond the Kuiper belt where Pluto makes its slow circuits, far beyond anything that our spacecraft have ever visited. The Sun would still be visible, still the brightest object in the sky, but it would be just a point of light now, no larger than a brilliant star, casting a feeble illumination that could barely be called daylight. And around you, scattered through the darkness at distances measured in millions of miles, would be countless billions of frozen objects, each one a relic of the solar system's formation, each one carrying memories of processes that occurred 4.5 billion years ago. This is the territory where Nemesis might be hiding, if it exists. This is the realm where a cold companion could drift for billions of years without being detected, without leaving any obvious signature in the data we collect from Earth. It is a place so vast and so empty that our intuitions fail us, where the distances between objects are so great that a traveller could journey for years without encountering anything at all. And yet it is not truly empty. It is filled with potential discoveries, with objects we have never seen, with mysteries we have not yet begun to solve. The search for Nemesis is, in a very real sense, a search into this territory, an attempt to pierce the veil that separates us from the outer reaches of our own solar system. Let us sit for a long moment with the scale of what we are discussing, because it is easy to use words like billions and trillions without truly grasping what they mean. The Oort cloud, if it exists as we imagine it, extends to distances of about 100,000 astronomical units from the Sun. 1 astronomical unit is the distance from the Earth to the Sun, about 93 million miles. So the outer edge of the Oort cloud is roughly 9 trillion miles away, a distance so vast that light itself takes more than a year to cross it. A spacecraft travelling at the speed of the Voyager probes, those distant ambassadors we launched in the 1970s, would take tens of thousands of years to reach the outer edge of the Oort cloud, and even then it would have explored only a tiny fraction of the volume, would have passed through a needle-thin corridor in a sphere of unimaginable size. This is the context in which the search for Nemesis must be understood. We are not looking for something hidden behind a nearby hill, something that a little more effort or a slightly better telescope might reveal. We are looking for something that might be hiding in a volume of space so vast that our entire civilization occupies less than a billionth of its extent. The search is not just difficult. It is, in the strictest sense, one of the most ambitious undertakings in the history of astronomy, an attempt to find a single object in a haystack larger than we can comprehend, and yet the search continues. It continues because the question matters, because the possibility matters, because the thought of that companion drifting through the darkness is too compelling to abandon. It continues because science is not a process that gives up when the answers are difficult, because the gradual narrowing of possibilities is itself a form of progress, because every null result brings us closer to the truth, even if the truth turns out to be nothing at all. The night has grown very quiet now, and the stars seem closer than they did before, and the thought of Nemesis has settled into that place where thoughts go when they do not need immediate resolution. It is a thought to carry forward, a question to hold in the mind without demanding an answer, a companion in its own right, even if the companion itself turns out not to exist. The search will continue, because that is what searchers do. And whether they find something or nothing, they will have done the work that matters, the work of looking, the work of wondering, the work of refusing to accept that the darkness is empty simply because we cannot see what fills it. There is one more thing worth understanding about the way this search has shaped our view of the cosmos, one more gift that the Nemesis hypothesis has given us even in its long decades of non-confirmation. It has taught us to look at empty space differently, to see absence not as negation but as possibility. Before Nemesis, the spaces between the stars were simply void, simply nothing, simply the backdrop against which the interesting objects performed their cosmic dance. After Nemesis, those spaces became hiding places, became potential refugees for objects we had not yet learned to see, became territories that might harbour companions we had not yet met. The hypothesis changed the way we think about nothingness itself, turned the darkness from an absence into a presence, from a void into a mystery. And this is perhaps the deepest contribution that the Nemesis hypothesis has made to our understanding of the universe, deeper even than the specific question of whether our sun has a companion. It has taught us humility about what we do not know, has reminded us that the visible universe is only the portion of reality that happens to announce itself to our instruments, and that beyond the edge of visibility there may be entire populations of objects going about their ancient business in perfect silence. The darkness is not empty, it is merely quiet, and quiet is not the same as absent. Consider for a moment the implications of this shift in perspective. For most of human history, we assumed that if something was important, we would be able to see it. The sun dominated our sky because it was the most important thing in our solar system, and the planets revealed themselves to our eyes because they mattered, because they were worthy of attention. The stars that we could not see with our naked eyes were assumed to be either very small or very far away, and in either case not particularly relevant to our immediate concerns. But the Nemesis hypothesis suggests something far more unsettling and far more wonderful. It suggests that there might be objects of enormous significance, objects that have shaped the entire history of life on Earth, objects that are as massive as the giant planets, or even more so, drifting through the darkness completely beyond our ability to perceive them. It suggests that the universe has secrets it has not yet told us, companions it has not yet introduced, and that our sense of knowing where we are and what surrounds us might be profoundly incomplete. This is not a frightening thought, not in the end. It is a humbling one, and humility before the cosmos is not the same as fear. It is more like wonder, more like the feeling a child has when they first realize that the world extends beyond the boundaries of their neighborhood, that there are places they have never been and might never go, that the map is not the territory, and the territory is far larger than any map could contain. The Nemesis hypothesis invites us to feel that wonder again, to remember that we are still explorers in a universe that has not yet revealed all its hiding places, still seekers in a darkness that may contain companions we have not yet met. It is worth pausing on the particular kind of object that Nemesis might be, because the possibilities have narrowed considerably over the decades of searching, and the picture that remains is both fascinating and strange. In the early days of the hypothesis, when it was first proposed in the 1980s, the assumption was that Nemesis would be a red dwarf star, a small, dim, but nonetheless active stellar body that would be detectable if only we knew where to look. Red dwarfs are the most common type of star in the galaxy, far more numerous than stars like our Sun, and they can be remarkably dim, producing only a tiny fraction of the light that our Sun produces. A red dwarf at the distance proposed for Nemesis would be invisible to the naked eye, would require a telescope to detect, but would nonetheless be well within the capabilities of modern astronomical surveys. The problem is that those surveys have been conducted. They have covered the entire sky multiple times, in multiple wavelengths of light, and they have found no red dwarf at the distance and with the orbital characteristics that the Nemesis hypothesis would require. If Nemesis were a red dwarf, we would have found it by now. The surveys have been too thorough, too sensitive, too comprehensive to have missed an object that bright. So the red dwarf version of Nemesis is essentially ruled out. The companion, if it exists, must be something dimmer, something harder to see, something that could hide in the data of those comprehensive surveys without revealing itself. And this is where the hypothesis enters truly fascinating territory, because the objects that remain as candidates are among the strangest and most elusive in all of astronomy. Picture, if you can, a brown dwarf, an object that occupies the uncertain boundary between planet and star. Brown dwarfs form the same way stars do, from the collapse of clouds of gas and dust, but they never accumulate enough mass to ignite the sustained hydrogen fusion that defines a true star. They are failed stars in a sense, objects that almost became suns but fell short at the final hurdle. They glow with a dim infrared light, the remnant heat of their formation slowly radiating away into the cold of space, and they fade over time as that heat dissipates, growing dimmer and cooler as the billions of years pass. A brown dwarf that formed alongside our Sun 4.5 billion years ago would be very cool by now, would have faded from the relatively warm temperatures of its youth to something much colder and much harder to detect. The WISE survey, that remarkable instrument that mapped the entire sky in infrared light, was specifically designed to find brown dwarfs, and it found many. It discovered thousands of these dim objects scattered through our galactic neighborhood, objects that had hidden from previous surveys, objects that announced themselves only in the infrared wavelengths that WISE was built to detect. And in doing so, it placed strict limits on what kind of companion our Sun might have. WISE would have detected a brown dwarf of Jupiter's mass or greater, out to a distance of about 26,000 astronomical units. It would have detected an object as massive as Saturn, out to a distance of about 10,000 astronomical units. These limits are not absolute certainties, but they are strong constraints, and they rule out the larger and warmer possibilities that once seemed plausible. But WISE could not see everything. It was sensitive to objects that emit infrared light, objects that are warm enough to glow in the wavelengths its instruments could detect. But it was not sensitive to objects that have cooled beyond a certain threshold, objects that have faded into a dimness that even infrared surveys cannot penetrate. And this is where the remaining possibilities live, in that twilight zone where objects are too cold to see, but too massive to ignore. Spare a thought too for the category of object that has emerged in recent decades as the most intriguing possibility for Nemesis, if Nemesis exists at all. These are sometimes called white dwarfs, the coolest and dimmest of all brown dwarfs. Objects that have cooled to temperatures comparable to a warm cup of coffee or even cooler, objects that emit almost no visible light and only the faintest traces of infrared radiation. White dwarfs are among the most difficult objects in the universe to detect, not because they are small, but because they are so cold, so dim, so reluctant to announce themselves to our instruments. And a white dwarf at the distances proposed for Nemesis, drifting through the outer darkness of the Oort cloud, would be essentially invisible to any survey we have conducted so far. This is the needle in the haystack that remains, the possibility that has not yet been ruled out. The haystack is vast, unimaginably vast, a sphere of darkness extending to the outermost reaches of the sun's gravitational influence. The needle, if it exists, is a cold, dim, ancient object that has been cooling for billions of years, that has faded from whatever warmth it once possessed into a state of near invisibility. And our instruments, for all their remarkable capabilities, have not yet developed the sensitivity to find such an object with certainty. We have narrowed the possibilities. We have ruled out the brighter candidates, the warmer companions, the objects that would have announced themselves to surveys like WISE. But we have not ruled out everything. The coldest, faintest possibilities remain in play, hiding in the data gaps that even our most comprehensive surveys cannot fill. There is something poignant about this state of affairs, something that speaks to the limitations of knowledge itself. We have looked as hard as we can look with the instruments we have built, and we have found nothing definitive, neither the presence nor the absence of a companion. The universe has declined to give us a clear answer, has left us in that uncomfortable middle ground where possibility lingers without resolution. And there is a lesson in this, a lesson about the nature of scientific inquiry and the patience it requires, a lesson about the difference between absence of evidence and evidence of absence. Return with me, one more time, to the question that started this whole investigation, the question of periodic extinctions, the patterns in the fossil record that first suggested something might be visiting the inner solar system on a regular schedule. Those patterns, as we discussed earlier, have not held up under scrutiny. The 26 million year cycle that seemed so compelling in the early analyses has faded into statistical noise as more data has been collected, as more sophisticated methods have been applied, as the original excitement has given way to careful reconsideration. The paleontological case for Nemesis, the case that first brought the hypothesis to prominence, is now regarded by most researchers as weak at best and spurious at worst. But here is the thing about scientific hypotheses, the thing that makes them different from other kinds of ideas. A hypothesis can be proposed for the wrong reasons and still turn out to be correct. The original motivation for an idea can be flawed, can be based on data that does not survive scrutiny, and yet the idea itself can remain valid. The question of whether the sun has a companion is not dependent on whether periodic extinctions are real. It is a question that stands on its own merits, that can be asked and investigated regardless of how it was first raised. The companion might exist even if the extinction patterns do not, because stars with companions are common in the universe, because our sun's apparent solitude is the exception rather than the rule, because the dynamics of stellar formation favour multiplicity over isolation. So the search continues, not because the original evidence was compelling, but because the underlying question remains open, remains interesting, remains worthy of investigation. This is the beauty of scientific inquiry, the way it can transcend its origins, the way it can continue to ask important questions even when the initial reasons for asking have fallen away. The Nemesis hypothesis is no longer primarily about explaining periodic extinctions. It has become something larger, a meditation on the hidden companions that might exist at the edges of our awareness, a reminder that the universe is under no obligation to reveal itself on our schedule, and we cannot leave this story without considering the instruments that might finally settle the question, the next generation of surveys and telescopes that might pierce the darkness where Nemesis could be hiding. The Vera C. Rubin Observatory, currently under construction in the mountains of Chile, will survey the entire southern sky repeatedly, searching for moving objects, for things that drift slowly against the background of fixed stars. It will be sensitive to much fainter objects than previous surveys, will be able to detect the slow motion of distant companions that earlier instruments would have missed. If Nemesis exists and crosses the southern sky, the Rubin Observatory might be the instrument that finally finds it, might be the eye that sees what has remained hidden for 4.5 billion years. But even the Rubin Observatory has limits. It cannot see what does not reflect or emit enough light, cannot find what has cooled below the threshold of detectability, cannot survey the vast volume of the Oort cloud in a single human lifetime. The search for Nemesis is not a search that can be completed quickly, not a question that can be answered with a single observation or a single survey. It is a search that will extend across generations, a question that will be passed from one cohort of astronomers to the next, a companion in itself even if the companion it seeks turns out not to exist. It is worth trying just once to feel what it would mean if Nemesis were found tomorrow, if some alert observer or some automated survey detected the telltale motion of a dim object at the distance the hypothesis predicts. The scientific community would erupt, of course. Papers would be written, conferences would be convened, observing time would be allocated on every major telescope on Earth and in orbit. The object would be studied intensively, its orbit would be calculated with increasing precision, and we would learn, finally, whether it poses any threat to the inner solar system, whether its gravitational influence reaches inward to disturb the comets of the Oort cloud, whether the Nemesis of myth has any connection to the companion of reality. But beyond the scientific excitement, beyond the papers and the conferences and the headlines, there would be something else, something quieter and more profound. There would be the realization that we were never alone, that for all the billions of years of Earth's history, there was a companion out there in the darkness, watching in its way, participating in its way, sharing the journey around the galactic center without ever announcing itself. We would have to revise our understanding of what our solar system is, would have to redraw the mental maps we carry of our cosmic neighborhood, would have to make room in our imagination for a presence we had never quite believed in. It would change something fundamental about how we see ourselves in the universe, not in a dramatic way, not in a way that altered our daily lives, but in a quiet way, in the way that all deep truths change us when we finally accept them. And if Nemesis is not found, if the searches continue for decades and centuries without success, if the limits tighten and tighten until there is no room left for even the coldest and dimmest companion, then we will have learned something equally valuable, equally important, equally worthy of the effort. We will have learned that our sun is truly alone, that the apparent solitude we observe is genuine rather than illusory, that whatever process formed our solar system did so in a way that was unusual, that bucked the statistical trends, that produced a single star where most produce pairs or triplets or larger families. This too would be a discovery, a truth worth knowing, a fact worth adding to our picture of who we are and where we came from. Either way, the search will have been worthwhile. Either way, the question will have been worth asking. And this is perhaps the most important lesson that the Nemesis hypothesis can teach us, the lesson that transcends the specific question of whether the sun has a companion. It is the lesson that asking is itself a form of discovery, that the process of searching is itself a form of finding, that every serious attempt to understand the universe brings us closer to truth, even when the immediate answer is no. The night is very deep now, and the stars seem impossibly distant, and the thought of Nemesis has settled into that contemplative place where thoughts go when they are too large for immediate resolution. Somewhere out there, perhaps, a dim companion is drifting through the darkness, has been drifting for billions of years, will continue drifting for billions more. Or perhaps the darkness is empty, is genuinely empty, contains nothing but the faint background of ancient starlight and the cold whisper of cosmic microwave radiation. We do not know which picture is correct, and we may not know for generations, may not know within the span of any human lifetime now alive. But the not knowing is not the same as ignorance. It is a different state entirely, a state of active wondering, a state of engaged uncertainty. We know the question. We know the methods by which the question can be investigated. We know the limits of our current instruments and the capabilities of the instruments to come. We are not stumbling in the darkness without a map. We are exploring the darkness with all the tools our civilization can muster, searching systematically, narrowing possibilities, closing in on an answer that the universe has not yet revealed. There is something deeply human about this enterprise, something that connects us to every generation of seekers who came before, to the astronomers who first trained their telescopes on the sky, to the navigators who first sailed beyond the sight of land, to the earliest members of our species who first looked up at the stars and wondered what they were. We are still those wanderers, still those seekers, still those creatures who cannot rest content with mystery when understanding might be possible. And whether Nemesis exists or not, that impulse to search, that refusal to accept the darkness at face value, is itself a kind of light, is itself a companion in the long journey through the cosmic night. Consider for a moment what it would mean to actually find it. Not the finding itself, not the technical achievement or the scientific validation, but the moment after, the long quiet moment when the announcement has been made and the data has been verified and the world has had time to absorb the news. Imagine waking up on that first morning in a solar system that is no longer quite what it was the day before, in a neighbourhood that has suddenly grown larger and stranger, that contains a presence you had never directly perceived. The sun would still rise as it always has, would still pour its light across the familiar landscape of your life, would still feel like the solitary guardian it has always seemed to be. But you would know, in a way you could not unknow, that there is something else out there. Something that has been there all along, something that shares the same ancient origin, the same primordial cloud, the same birthday in the deep history of the galaxy. You would be living in a binary system, would have always been living in a binary system, would simply have been unaware of this fundamental fact about your cosmic address for the entire span of human history. It is worth trying, just once, to feel what that awareness might do to a person. Not everyone would feel it strongly. For many, perhaps most, the news would register as an interesting fact, a headline glimpsed and then forgotten, a piece of trivia to mention at dinner parties before moving on to more immediate concerns. The companion would be too distant to see, too cold to warm anything, too faint to photograph with any backyard telescope. It would remain an abstraction, a number in a database, a dot on a chart in a scientific paper that most people would never read. Life would continue in all its familiar rhythms, unaltered by the knowledge that the sun is not alone. But for some, for those who carry the night sky inside them, for those who have spent their lives looking up and wondering, the discovery would land differently. It would settle somewhere deep, in that place where our sense of home is stored, and it would gently rearrange the furniture of the soul. To learn that your star has a sibling is to learn that you have been part of a larger family all along, that the isolation you perceived was a function of distance and dimness rather than genuine solitude. It is to realize that the story of your solar system was always more complicated than you knew, that there were chapters you had never read, characters you had never met, and even if that sibling is cold and dark and impossibly far away, even if it will never influence your life in any measurable way, the knowledge of its existence would change the texture of your aloneness. You would be alone in the way that a person is alone in a large house, where someone else is sleeping in a distant room, not in the way that a person is alone in an empty house on an empty street in an empty town. The presence would matter, even if it never made a sound. Return with me, one more time, to the people who have devoted their careers to this question. They are scattered across universities and research institutions around the world, astronomers and astrophysicists and data analysts who have spent years staring at infrared surveys and proper motion catalogues and the statistics of stellar populations. Some of them believe that Nemesis is likely, that the evidence for a companion remains compelling despite the negative results of the major searches. Others believe that the hypothesis has been effectively ruled out, that the parameter space has been squeezed too tightly for any plausible companion to hide. Still others occupy the uncertain middle ground, the agnostic position that holds both possibilities open, that waits for better data before reaching a conclusion. They argue with each other at conferences, publish papers that respond to each other's papers, send emails late at night when a new idea strikes them. They are engaged in the ancient and noble work of trying to figure out the truth about something that matters, and they do this work with all the rigour and passion and occasional pettiness that characterises any human endeavour. What unites them, across their disagreements, is the seriousness with which they take the question. None of them treats the Nemesis hypothesis as a joke, as a piece of science fiction that somehow wandered into the journals, as a topic unworthy of careful investigation. They understand that the question of whether our sun has a companion is a real question with a real answer, an answer that exists independently of our ability to determine it, an answer that the universe knows even if we do not. And they understand that finding this answer, or narrowing the possibilities until an answer becomes clear, is work that matters, work that adds to the slowly accumulating structure of human knowledge about the cosmos we inhabit. There is one more thing worth understanding about why this particular search has proven so difficult, and it has to do with the nature of the objects we are looking for. Brown dwarfs, the most likely candidates for a cold and dim companion, are strange creatures by stellar standards. They are born the same way that stars are born, from the collapse of gas and dust in molecular clouds, from the same processes of gravitational contraction that produced our sun and every other star in the sky. They begin their lives hot and glowing, radiating the heat of their formation into the darkness, looking for all the world like small red stars on the threshold of ignition. But they never cross that threshold. They never quite manage to ignite the nuclear fires that would make them true stars, that would give them the sustained brilliance that powers our sun and every other member of the stellar main sequence. They're too small, their cores too cool, their gravitational pressure too weak to force hydrogen nuclei together at the rates required for sustained fusion. They are, in a sense, failed stars, stars that almost made it but fell short, stars that will spend eternity slowly cooling and fading into the dark. This is not a failure in any meaningful sense, of course. It is simply what they are, what the physics of their mass and composition destines them to be. A brown dwarf does not know that it is not a star, does not feel the absence of nuclear fire, does not mourn the brilliance it will never achieve. It simply exists, radiating away the heat of its formation over billions of years, growing colder and dimmer with each passing eon. And this slow cooling is precisely what makes brown dwarfs so difficult to detect, what makes them such effective hiding places for a hypothetical companion like Nemesis. A brown dwarf that formed alongside our sun some 4.5 billion years ago would have had billions of years to radiate away its birth heat. It would have started hot, would have glowed brightly in the infrared for millions of years, would have been easily visible to our instruments if we had been around to point them in the right direction. But we were not around. We would not be around for billions of years, would not develop infrared telescopes for billions of years after that. By the time we began searching, the brown dwarf would have cooled to a whisper of its former warmth, would have faded to temperatures that challenge even our most sensitive detectors. The mathematics of this cooling is relentless. A brown dwarf with perhaps 50 times the mass of Jupiter, formed at the same time as our Sun, would now have a surface temperature of perhaps 300 Kelvin, roughly room temperature by human standards. It would glow faintly in the deep infrared, at wavelengths our eyes cannot perceive, at intensities our instruments can barely measure across the distances involved. A smaller brown dwarf, perhaps 20 or 30 times the mass of Jupiter, would be colder still, perhaps 250 Kelvin, perhaps cooler, depending on its exact mass and composition. And below a certain mass threshold, the objects we call brown dwarfs shade into the objects we call planetary mass objects, bodies that never had any chance of ignition, that were always destined to be cold and dark, that might cool to temperatures below 100 Kelvin over the age of the solar system. These coldest objects, sometimes called white dwarfs or sub-brown dwarfs, are the darkest hiding places of all, the corners of parameter space where even our best infrared surveys struggle to see. Spare a thought too for the sheer volume of space that must be searched. If Nemesis exists at the distances suggested by the original hypothesis, somewhere between 1 and 3 light-years from the Sun, it occupies a sphere of space that is almost inconceivably vast. A light-year is roughly 6 trillion miles, roughly 10 trillion kilometers, roughly 63,000 times the distance from the Earth to the Sun. The volume of a sphere scales with the cube of its radius, which means that the volume of space between 1 and 3 light-years from the Sun is enormous, is measured in cubic light-years, is larger than the human mind can meaningfully visualize. Searching this volume thoroughly, checking every point for the faint infrared signature of a cold brown dwarf, is a task that strains even our most ambitious surveys. It is like searching a darkened warehouse the size of a city for a single cooling ember, using only a narrow beam of infrared light that can illuminate one small area at a time. The ember might be there, might be glowing faintly somewhere in the vastness, but finding it requires patience, requires systematic coverage, requires instruments sensitive enough to detect the faint warmth against the cold background of space. And we cannot leave this story without considering the possibility that Nemesis, if it exists, might not be a brown dwarf at all. The original hypothesis, as proposed by Davis, Hutt and Muller in 1984, suggested a red dwarf star as the companion, a small but genuine star that would be visible to optical telescopes despite its distance. This version of Nemesis was ruled out almost immediately, because a red dwarf at the proposed distance would be easily visible, would have been catalogued long ago, would appear in our star charts as a known member of the solar neighbourhood. But between a red dwarf and a brown dwarf lies a range of possibilities, objects that might be technically classified as stars but that are so dim and so cool that they approach the brown dwarf boundary. The coolest red dwarfs, the smallest and faintest true stars, have surface temperatures of perhaps 3000 Kelvin and luminosities perhaps 1/10,000th that of the Sun. They are visible to our surveys, are well catalogued in our stellar databases, are not plausible candidates for an undiscovered companion at the distances we are considering. But what about objects even cooler than these? What about the strange creatures that exist at the boundary between stars and brown dwarfs? The objects that may or may not sustain weak hydrogen fusion in their cores? The objects whose classification remains uncertain, even to the experts who study them? What about the possibility that Nemesis is something genuinely unusual, an object that does not fit neatly into our existing categories, an object that our surveys might overlook precisely because it does not match the signatures we expect? This is a speculative possibility, a long shot by any reasonable assessment, but it is not completely ruled out. The universe has surprised us before with objects that defied our expectations, with phenomena that fell between the cracks of our classification schemes, with discoveries that expanded our understanding of what is possible in the cosmos. A truly unusual companion, something that does not behave like a typical brown dwarf or a typical star, might evade detection in ways we have not anticipated. Let us sit for a long moment with the thought that the search itself has value, regardless of its outcome. There is a tendency in our culture to measure the worth of scientific investigations by their results, to celebrate the discoveries and quietly forget the null results, to remember the experiments that found something and overlook the experiments that found nothing. This tendency misunderstands the nature of scientific progress, misunderstands the way that knowledge accumulates over time, misunderstands the essential role that negative results play in narrowing the space of possibilities. When the WISE satellites surveyed the infrared sky and found no evidence of a bright brown dwarf companion to the Sun, this was not a failure. It was a success, a genuine contribution to our understanding, a piece of information that constrains our models and guides our future searches. We now know something we did not know before the survey, something that the universe told us through the absence of a signal, something that shapes our expectations and refines our hypotheses. The null result is itself a result, is itself a form of discovery, is itself a stepping stone on the path toward truth. And the same will be true of future searches, regardless of their outcomes. If the next generation of infrared telescopes surveys the solar neighbourhood with unprecedented sensitivity and finds a cold brown dwarf at 2 light-years from the Sun, we will celebrate the discovery, will marvel at the confirmation of the Nemesis hypothesis, will rewrite our textbooks to include the Sun's long-hidden companion. But if those telescopes find nothing, if they push the limits even further and still come up empty, we will celebrate this too. We'll marvel at the confirmation that our Sun is truly alone. We'll rewrite our textbooks to explain why our solar system differs from the binary norm. Either outcome adds to our knowledge, either outcome teaches us something true about the universe, either outcome justifies the effort and expense of looking. It is worth pausing on the simple fact that we can ask this question at all. For most of human history, the idea of searching for a companion to the Sun would have been meaningless, would have been literally unthinkable, would have required concepts and instruments and theoretical frameworks that did not exist. The ancient astronomers who first named the stars and tracked the planets across the sky had no way to conceive of brown dwarfs, had no infrared detectors, had no understanding of stellar formation or nuclear fusion, or the physics that distinguishes a star from a failed star. They looked up at the same sky we look up at tonight, saw the same patterns of light against the darkness, wondered about the same mysteries of distance and composition and origin. But they could not ask whether the sun has a companion, because they lacked the conceptual vocabulary to frame the question, lacked the instrumental capabilities to investigate it, lacked the theoretical background to interpret whatever answers they might have found. We are the inheritors of 4 centuries of telescopic astronomy, of 2 centuries of spectroscopy and photometry, of decades of space-based observation and infrared survey work. We stand on the shoulders of thousands of researchers who came before us, who built the instruments and developed the theories and gathered the data that make our current searches possible. The question of whether the sun has a companion is a question we can ask precisely because so many people work so hard to give us the tools for asking it, to expand the boundaries of what is knowable, to push back the darkness of ignorance one careful observation at a time. Picture, if you can, the people who built the WISE satellite, the engineers and technicians and project managers who turned a concept into a functioning spacecraft, who solved the 1,000 technical problems that stood between the idea and its realization. They worked in clean rooms and testing facilities, in offices and laboratories, in all the unglamorous spaces where space missions are actually assembled. They worried about cooling systems and detector sensitivity, about launch vibrations and orbital mechanics, about data transmission rates and instrument calibration. They spent years of their lives on a project whose purpose was to survey the infrared sky, to see what had never been seen before, to search the darkness for objects that might be hiding there. Many of them probably never thought specifically about Nemesis, never connected their daily work to the question of whether the sun has a companion. They were doing their jobs, solving their problems, contributing their expertise to a larger endeavour whose full implications they might not have considered. But their work made the search possible, made it real, transformed the Nemesis hypothesis from a theoretical speculation into a testable prediction that could be confronted with data. This is how science actually works, not as a series of dramatic discoveries by lone geniuses, but as a collective enterprise involving thousands of people whose contributions may be invisible to the public, whose names may never appear in the headlines, whose daily efforts nevertheless push the boundaries of human knowledge forward. The search for Nemesis is carried by this collective effort, by the astronomers who analyse the data, and the engineers who build the instruments, and the theorists who develop the models, and the administrators who secure the funding, and the educators who train the next generation of researchers. It is a human enterprise in the fullest sense, a project that draws on the accumulated wisdom and capability of our entire civilization. There is a smaller, quieter story woven through all of this, the story of a single night of observation, a single moment when an astronomer somewhere sat before a computer screen and examined the data from a survey that might, just might, contain evidence of the sun's companion. Perhaps it was late at night in a university office or a home study, the kind of hour when the world is quiet and concentration comes easily. Perhaps the astronomer had been working on this project for years, had examined thousands of similar data points, had developed an intuition for what normal looked like and what might be anomalous. Perhaps there was a moment of excitement, a sudden quickening of the pulse, when a data point appeared that seemed slightly different from the others, that had a proper motion or an infrared signature that warranted a closer look. Perhaps the astronomer leaned forward, felt the ancient thrill of possible discovery, allowed herself to imagine for just a moment that this might be the one, that this might be the data point that changed everything. And perhaps, after careful examination, the data point turned out to be something mundane, a distant galaxy or a known asteroid or an instrumental artifact, one more false alarm in a long series of false alarms. Perhaps the astronomer leaned back, felt the familiar mixture of disappointment and determination, made a note in the log and moved on to the next data point. This is what the search actually looks like, night after night, year after year, the patient accumulation of examined possibilities, the gradual narrowing of the parameter space, the slow approach toward a truth that the universe will reveal in its own time. The night is very deep now, and the stars have not moved visibly since we began, though they have travelled enormous distances through the galaxy, carrying us with them on their long journey around the galactic centre. Somewhere in that darkness, in the vast spaces between the stars, the question of Nemesis remains open, remains unresolved, remains one of those mysteries that we carry with us into sleep without knowing whether the morning will bring answers. The companion might be there, might be drifting at this very moment through the cold reaches of the outer solar system, a dark presence that has been with us since the beginning but has never been seen. Or the companion might not be there, might be a phantom born of pattern-seeking and statistical anomaly, a story we told ourselves that turned out to be fiction rather than fact. We do not know. We may not know for a long time. But the not knowing is itself a kind of knowledge, an honest acknowledgement of the limits of our current understanding, a recognition that the universe is larger and stranger and more full of possibility than we can easily comprehend. And in that not knowing, there is something that feels almost like peace. Consider for a moment the particular quality of astronomical uncertainty. When we say we do not know whether Nemesis exists, we are not expressing ignorance in the ordinary sense. We are not saying that we have failed to look, or that we lack the will to find out, or that the question lies beyond the reach of human inquiry. We are saying something far more interesting. We are saying that we have looked with extraordinary care, with instruments of remarkable sensitivity, across years and decades of patient observation, and the universe has given us an answer that is neither yes nor no. It has given us a maybe that is bounded, that is constrained, that occupies a specific region of possibility space that we can describe with precision even as we cannot resolve it with certainty. This is a different kind of not knowing than the not knowing of our ancestors, who looked at the same stars and wondered what they were made of, whether they were near or far, whether they might harbour worlds of their own. We have answered those questions. We have measured the distances to millions of stars, determined their compositions from the light they emit, discovered thousands of planets orbiting them. We have extended our knowledge so far into the darkness that the remaining mysteries are themselves testaments to how much we have learned. The question of Nemesis persists not because we have been careless or lazy or insufficiently curious, but because the universe is genuinely difficult to search, because the coldest and dimmest objects hide themselves from even our most sensitive instruments, because the outer reaches of our own solar system remain, in some ways, as unexplored as they were when humans first looked up at the night sky and wondered what was out there. It is worth trying, just once, to feel what that search has actually meant for the people who have conducted it. The astronomers who have spent careers pursuing this question did not do so because they expected to find Nemesis. They did so because the question was interesting, because the possibility was real enough to warrant investigation, because the act of looking is itself a form of participation in the great human project of understanding our place in the cosmos. Many of these researchers have published papers that narrowed the constraints, that ruled out certain possibilities, that contributed to our collective understanding without ever delivering the dramatic discovery that might have made their names famous. Their work was essential, their contributions genuine, their dedication admirable, even though the answer they found was not here rather than here it is. Science honours such work, recognises it as the foundation upon which all discovery is built, even though the public imagination tends to celebrate only the breakthroughs and overlook the patient labour that made them possible. The search for Nemesis has been a training ground for techniques that will be used in other searches, a testbed for instruments that will discover other objects, a school for astronomers who will go on to make other contributions. Even if Nemesis is never found, even if the hypothesis eventually fades from active consideration, the search will have been worthwhile for what it taught us about how to look for faint, cold, distant objects in the darkness between the stars. Return with me, one more time, to the circumstances of stellar birth, to those molecular clouds where suns are kindled and where the question of Nemesis first arises. When we observe young stellar systems today, we see a remarkable variety of configurations. Some stars are born alone, emerging from their natal clouds as solitary wanderers who will never have close companions. Some are born in pairs, bound together by gravity from their earliest moments, destined to orbit each other for billions of years. Some are born in larger groupings, clusters of dozens or hundreds or thousands of stars that gradually disperse over millions of years, as the gravitational ties that bound them together are loosened by encounters with other stars and by the slow stretching of orbital dynamics. Our Sun, if it was born with a companion, was born in one of the more loosely bound configurations, a wide binary that might have persisted for millions of years before dissolving, or that might have held together for longer, carrying Nemesis outward as our solar system moved through the galaxy. The molecular cloud that gave birth to our Sun is long gone, dispersed by the radiation and winds of the young stars it created, its material incorporated into the next generation of stellar nurseries, its memory preserved only in the chemical signatures of the planets and asteroids and comets that remain. We cannot go back and observe our own stellar birth, cannot rewind the tape and watch to see whether a second point of light kindled alongside our sun in that ancient cloud. We can only look at the evidence that remains, the subtle clues in the present that might point toward an invisible companion, and ask whether the pattern fits. Picture, if you can, what Nemesis might look like if it exists. Not a star in the ordinary sense, not a point of brilliant light against the darkness, but something far more subtle, far more difficult to see. A brown dwarf at the distance of the inner-Oort cloud would appear as a faint point of infrared warmth against the absolute cold of interstellar space, detectable only by instruments specifically designed to see in wavelengths the human eye cannot perceive. Its surface, if we can call it a surface, would be a turbulent atmosphere of hydrogen and helium, perhaps with clouds of ammonia or water ice, perhaps with bands and storms like those of Jupiter, but on a much larger scale. Its interior would be warm, heated by the slow contraction of its own mass and by whatever nuclear reactions it can sustain at its modest core temperature, but not warm enough to shine as a true star, not bright enough to announce itself across the light years. At a distance of perhaps 1 trillion miles or more, this object would move against the background stars with a proper motion so small that years of observation would be required to detect it, decades perhaps to measure it accurately enough to determine whether it is bound to our sun or merely passing through. It would be a patient presence, unhurried, unannounced, keeping pace with our solar system on its long journey around the galaxy, without ever drawing attention to itself, without ever disturbing the orderly motions of the inner planets, without ever doing anything dramatic enough to force us to acknowledge its existence. If it is there, it has been there for 4.5 billion years, has watched from a great distance as the planets formed and cooled, and life arose on at least one of them, has been a silent witness to the entire history of our world without ever intervening in that history, without ever making its presence known. It would be the oldest inhabitant of our stellar neighbourhood that we have never met, a sibling who left home before we were aware enough to remember, who has been nearby all along without ever knocking on the door. Spare a thought too for the future of this search, for the instruments and surveys that will continue to probe the darkness in the years and decades to come. The James Webb Space Telescope, launched in late 2021, has opened new windows on the infrared universe, has revealed details of distant galaxies and nearby star-forming regions that were invisible to earlier instruments. Its sensitivity to faint infrared sources is unprecedented, its ability to resolve fine details in the darkness unmatched by any previous observatory. Surveys conducted with Webb and its successors will continue to narrow the constraints on what might be hiding in the outer solar system, will continue to push the limits of detectability toward ever colder and ever more distant objects. The Vera Rubin Observatory, under construction in Chile, will conduct a systematic survey of the entire visible sky, with a sensitivity and cadence that will reveal moving objects throughout the solar system, will track the motions of millions of asteroids and comets and potentially undiscovered planets, will build a map of the moving universe more complete than anything we have ever possessed. These instruments will not be searching specifically for Nemesis, but they will be capable of detecting it if it crosses their fields of view, if it is bright enough and moves fast enough to stand out against the background of distant stars. The search will continue not as a dedicated mission, but as a byproduct of our general curiosity, a natural consequence of our determination to catalogue and understand everything we can see. And perhaps someday one of these surveys will find something, a faint point of light that moves in just the right way, that has just the right infrared signature, that turns out upon further investigation to be something we have been wondering about for decades. Or perhaps not. Perhaps the surveys will continue for another century without finding anything, will gradually rule out ever smaller and ever colder companions, will eventually bring us to a point where we can say with confidence that the Sun is truly alone, that the companion hypothesis was clever but incorrect, that the patterns that first suggested it were coincidences after all. Let us sit for a long moment with the thought of what it would mean if Nemesis does not exist, if the search eventually concludes without a discovery. This would not be a failure. It would be an answer, a genuine contribution to human knowledge, a truth about our solar system as valuable as any discovery. To know that the Sun is alone, that it was born without a companion, or lost that companion so early and so completely that no trace remains, would tell us something important about the circumstances of our origin, about the probability of wide binary formation in molecular clouds like the one that gave birth to our Sun, about the dynamics that shape stellar families in the first millions of years of their existence. It would close a chapter of inquiry, would allow the resources and attention devoted to this search to be redirected toward other questions, would provide a settled answer where previously there was only uncertainty. The absence of Nemesis would be a discovery in its own right, a negative result with genuine scientific value, a piece of the puzzle of our cosmic context that we did not possess before. Science makes progress through such negative results, through the patient elimination of possibilities, through the gradual narrowing of the space of what might be true until what is true stands revealed. If Nemesis does not exist, then the search for it will have taught us that, and that teaching will have been worth the effort. And we cannot leave this story without acknowledging the deeper question that underlies all of this, the question of why we search at all, why we care whether the Sun has a companion, why the possibility of Nemesis has captured the imagination of astronomers and the public alike for 4 decades. The answer, I think, has to do with our deep need to understand our origins, to know where we came from, to place ourselves in a context that extends beyond the brief span of human history into the cosmic timescales on which stars are born and planets form and life emerges. We search for Nemesis because we want to know who our cosmic relatives are, whether we are alone in our immediate stellar neighbourhood, whether our Sun is an only child or one of a family that has been scattered by time and distance. The question touches something fundamental about human identity, about our sense of belonging in a universe that can seem cold and empty and indifferent to our existence. To find a stellar sibling, even a cold and distant one, would be to discover that we are less alone than we thought, that our Sun has company on its long journey through the galaxy, that there is another member of the family out there in the darkness, keeping pace with us even if we never exchange signals or visit each other across the vast distances that separate us. This is not a scientific motivation in the strict sense, but it is a deeply human one, and it helps to explain why the Nemesis hypothesis has persisted in the imagination long after many other astronomical hypotheses have been forgotten. There is one more thing worth understanding about the nature of this search, about the quality of patience it requires, and the kind of hope it permits. The astronomers who look for Nemesis do not expect to find it tomorrow, or next month, or even next year. They work on timescales that are measured in decades, that extend beyond individual careers and individual lifetimes, that involve passing the work from one generation of researchers to the next. This is the pace of deep astronomical inquiry, the rhythm of questions that cannot be answered quickly, that require sustained attention across spans of time that feel long by human standards but are brief by cosmic ones. The search for Nemesis has already spanned 40 years, from the first proposals in the early 1980s to the present moment. It may span another 40 years or another century before it reaches a conclusion one way or the other. The researchers who began this work are passing it to younger colleagues, who will pass it to colleagues younger still, in a chain of transmission that connects the curiosity of one generation to the discoveries of the next. This is how science moves forward on the largest questions, the questions that cannot be answered in a single human lifetime, the questions that require the sustained commitment of a civilization rather than the heroic effort of a single individual. If Nemesis is ever found, the discovery will belong to everyone who contributed to the search, to the entire community of astronomers and engineers and theorists who made the instruments and analysed the data and refined the models over decades of patient work. So let us ask it directly, one final time, as the night deepens and the stars wheel slowly overhead. Is the Sun alone, or does it have a stellar sibling somewhere in the outer darkness, a dim companion that has travelled with us since the beginning but has never been seen? The honest answer is that we do not know. The surveys have ruled out the brightest candidates, have narrowed the parameter space considerably, have pushed the limits of detectability toward ever colder and ever more distant objects. But they have not closed the question. There remains a region of possibility space that has not been fully explored, a range of masses and temperatures and distances where a companion could still hide, where the coldest brown dwarfs and the most distant orbits remain beyond the reach of current instruments. Nemesis might be there, a patient presence that has accompanied our Sun through 4.5 billion years of cosmic history, without ever announcing itself. Or Nemesis might not be there, might be a phantom born of coincidence and pattern seeking, a hypothesis that seemed promising but turned out to be incorrect. We do not know. And in that not knowing, we find not frustration but invitation, not failure but the promise of continued discovery, not an ending but an opening toward future understanding. But silence is not the same as absence. If Nemesis exists, it is out there tonight, drifting through the cold reaches of the outer solar system, growing more distant with every breath you take. It has been there since before the Earth formed, since before the first continents rose from the ancient oceans, since before the first stirrings of life in the warm, shallow waters of a younger world. It has been a companion to our sun through all the ages of cosmic and biological and human history, a silent presence that has witnessed everything without ever being witnessed in return. It does not know that we are looking for it, does not know that we have wondered about its existence, does not know that somewhere on a small rocky world, orbiting its stellar sibling, beings have evolved who can ask questions about the nature of their cosmic family. It simply drifts, patient and cold, following the gentle gravitational threads that bind it to our sun across distances too vast for human intuition to grasp. And if it does not exist, if the search eventually concludes with certainty that our sun is alone, then we will know that too, and that knowledge will be its own kind of comfort. We will know that the patterns that first suggested a companion were coincidences, that the extinction periodicity was a statistical artifact, that our sun emerged from its natal cloud as a solitary wanderer who has made this long journey through the galaxy without the company of a stellar sibling. We will know that we're truly alone in our immediate cosmic neighbourhood, that the nearest stars are strangers rather than family, that our sun is an only child who has done well enough on its own. This too would be an answer, a genuine piece of knowledge about our origins, a truth that we did not possess before. Either way, the search will have been worthwhile. Either way, the questions will have mattered. Either way, the patient work of generations of astronomers will have contributed to human understanding of our place in the cosmos. The night is very quiet now. The stars continue their slow wheeling overhead, following paths that were ancient when the first humans looked up at them and wondered what they were. Somewhere among those stars, or in the dark spaces between them, the truth about Nemesis waits to be discovered. It will reveal itself in its own time, at its own pace, when our instruments are sensitive enough, and our surveys are complete enough, and our patience has been rewarded with the clarity that only sustained inquiry can provide. Until then, we carry the question with us, a companion of a different kind, a mystery that accompanies us through the darkness without demanding resolution. We do not need to know the answer tonight. We only need to know that the question is real, that the search is genuine, that somewhere out there the universe holds a truth about our stellar family that we have not yet discovered. Perhaps that is enough. Perhaps the wondering is itself a form of connection, a way of reaching out across the vast distances to touch something that may or may not be there, to acknowledge the possibility of a companion even if we never meet. Perhaps the search for Nemesis is its own reward, a meditation on origins and belonging and the nature of cosmic solitude that enriches us whether or not it ever reaches a conclusion. The companion might be there, the companion might not be there, we do not know, but we are still looking, and there is something beautiful in that. Thank you for travelling out to the edge of our stellar neighbourhood with me tonight, to the cold and quiet places where the oldest questions still wait for answers. Whatever is out there in the darkness, whatever truth the universe is holding for us, I hope you carry a little of this wandering with you into sleep, a small companionship of curiosity to keep you company until morning. Keep looking up, take